Chapter 3, problem number 17. A hot air balloon is rising straight up with a speed of 3 meters per second. A ballast bag is released from rest relative to the balloon when it is 9.5 meters above the ground. How much time elapses before the ballast bag hits the ground? So the story begins when the ballast bag is released. Relative to the ground, the ballast bag is traveling at the velocity of the balloon, which is 3 meters per second. So given information, we have VO is equal to 3 meters per second. The ballast bag, like anything else in free fall, will accelerate at 10 meters per second squared, and this is down. The ballast bag is initially going upward, just like the balloon. And the location of the ballast bag at the beginning of the story is equal to 9.5 meters above the ground. So that's positive 9.5 meters. They want to know how much time it takes the ballast bag to hit the ground. So the final position of the ballast bag is 0 meters, and then the unknown is time. Okay, so a diagram to go along with this would look something like this. Here's the ballast bag. It's traveling upward initially. It's accelerating downward. The upward direction is positive. The original position, YO, and the final position, 0 meters. As far as an equation, we know VO, G, Y original, Y final. We're looking for time. Well, we have the equation that the vertical displacement is equal to the original velocity times time plus 1/2 the acceleration due to gravity times the time squared. So we're going to solve this for time. Okay, solving this for time, we get delta T. So it's a quadratic equation, and this is the quadratic solution to that equation. Okay, substituting negative VO, so we have negative 3 meters per second, plus or minus the square root of 3 meters per second squared, minus 4 times 1/2. G is negative 10 meters per second squared, times negative 1 times delta y would be YF, which is 0 minus Y original, which is 9.5 meters. And then this is all divided by negative 10 meters per second squared. So here we go. Let me figure out what's under the radical first. So I get 199. Now I'm going to take the square root of that, and I get 14.11 approximately. Now I'm going to put that into memory. Now I'm going to take -3, and I have to think. I'm going to add -3 to what I have in memory, and then I have to divide it by -10. Now I want a positive time, so I'm going to add, because if I take -3 plus what I have in memory, I get a positive number. Divided by a negative number, no, I get a negative time. So I have to subtract. You see my thinking there. I had to look at both positive and negative and see which will give me a positive time. So I'm going to take -3, and I am going to subtract what's in memory, which is 14.11 approximately. And now divide that by -10, and I get 1.7 seconds. Now, suppose you didn't know the quadratic solution and you didn't know how to solve the vertical displacement is equal to the original velocity of the ballast bag times the time of fall plus 1/2 the acceleration due to gravity multiplied by the time squared. Well, we have another approach. We can use another equation. Okay, so let's start with the vertical displacement is equal to the original velocity plus the final velocity divided by 2 multiplied by time. And solve this for time. So we get delta t is equal to 2 times delta y divided by the original velocity plus the final velocity. So we know delta y, that's yf minus yo. We know VO, that's positive 3 meters per second. But we don't know VF. So I'm going to go to another equation. And I'm going to go to VF squared is equal to VO squared plus 2G delta Y. And I'm going to solve that for VF. Now, I know it's going downward, so I'm going to choose the negative answer. So we have VF then is equal to the negative of the square root of VO squared plus 2G delta Y, which is YF minus YO. Now I'm going to substitute that into this expression. And now I can put in the values. So I have 2 times delta y, which is yf minus yo. Let me change that here. So we have 2 times 0 minus 9.5 meters divided by 3 meters per second minus the square root of 3 meters per second squared plus 2 times negative 10 meters per second squared times 0 minus 9.5 meters. Let's see what we get. So I'm going to do the denominator first. Get 190, now I have to take the square root of that, and I get 13.78. I am going to subtract that from 3, and then I'm going to divide that into 9.5 times 2. Negative 9.5 times 2. And I get 1.76 seconds, just like I did before. I just checked my work, and this actually turns out to be 1.71 second. I'm now going to draw the corresponding motion graphs for the ballast. Well, the ballast, upon release, is in free fall. So I'm going to draw a straight line parallel to the t-axis. So that represents g. For velocity versus time, the ballast starts out with a velocity equal to that of the balloon, and it's directed upward, and then it immediately starts to decelerate. When it reaches its highest point, it's at rest, and then it starts to fall again. For the position versus time graph, the ballast starts above the ground at a position y original. So I start out with a positive slope, and then it flattens out here, and then the ballast starts to fall back down to the ground. So this corresponds to VF, this is VO, this is TF, the end of the story. This corresponds to the highest point.